Hey everybody! So we're back. We're going to do a little bit more in depth with Weka today. What we're going to start with is looking at the same data that we had last time on the real estate prices. So I have that loaded up in Excel here. This is the same file that we had in class last week, so you can download that. And in the example that we did in class last week, we were doing classification on this last column, which I actually made up to say whether or not the house was priced in the millions or not. That was a classification problem. So we were looking at taking this data and seeing if we could classify each house into the $1 million home or not category. What we're going to start with today is actually a regression problem. So you remember a couple weeks ago we did linear regression where we had a bunch of variables, and essentially what we were trying to do is come up with a prediction of our dependent variable by weighting each of our independent variables. And you can actually do exactly that kind of linear regression in Weka and much more complex types of regression as well. So the difference between regression and classification is that classification puts stuff in categories and regression comes up with a number. So we're going to take this data, but instead of using this last column, we're going to use the price column. So we're going to try to predict the price of a house based on the other things we know about it. In this case, we'll look at the zip code, the number of bedrooms, bathrooms, half baths, the category of home that it is, so single family or condo, the size in square feet, and the lot size. So we're going to ignore the address. This ID doesn't have any meaning, and so we're just going to take these categories. And we'll take the price as well. I'm going to copy that, and we're going to do the same thing we did last time. We're going to make a Weka ARF file, ARFF file, from this. So I always copy my data directly out from Excel. We're over here now in Text Wrangler, but you can use any plain text editor. And I'm going to put the data heading on this and paste in my data. So there's a couple steps that we want to take here to make sure this data is cleaned up. I don't know if you noticed, but there are some blank columns over here. This is one, here's another one, and Weka cannot handle missing data. Now I think all the blank columns are in lot size, and it makes sense for condos that there's not necessarily a lot size. So what we're going to do here, and you could also do this in Excel, is to find those blanks and fill them in. I'm going to look for two tabs because this is tab separated data, and I'm going to replace those with a tab and then a 0 and another tab. So the two tabs basically indicate there's a tab and another one, so we've gotten to a place where we're supposed to see a value and that value is missing. And this is going to put a 0 in between those tabs, essentially filling in that space. So I'll replace all of our missing values, and there were a whole bunch, with 0. Now that gets all of our data taken care of. What we want to do next is put the heading on this. So I'm going to scooch this down just so we can see the headings here in Excel, which will be helpful. Remember, we start off with this label relation and then some name for what it is that we're trying to predict. The name of this doesn't matter. It can be anything you want. The next thing we do is list our attributes. So we're going to have an attribute, and then these are the headings for each of the columns we have here. They don't have to match what we have in Excel. They should just be sort of descriptive. So if we try to get information about that out later, which we'll see here, we know what we're talking about. So we'll have zip code, and that's numeric. And in fact, all of our data is going to be pretty much like that. So I'm just going to copy and paste this. We'll have bedrooms, full, half baths, a type, a size, a lot size, and a price. I'm going to change all of these. So bedrooms, bath, half bath. I'm just matching the column names here. Type, we're going to have to come back and deal with because it's not numeric and it's really weird. So we'll fix all that up. But we'll finish the rest of these first. Okay, so now we have everything labeled here. Our file is basically set. All we need to do is deal with this type. So there's a bunch of stuff in here. This is not clean, nice data. So the first thing that we're going to do is get rid of the word family home. We want a nice single word descriptor for the type. So there's multifamily homes and single family homes. Let's just get rid of family home. I'm just going to search for it, replace it with nothing. So that gets taken care of. We'll do the same thing here for condos. It's like condos, townhomes, row homes, etc. We're going to get rid of everything after condo the same way. Just search for that, replace it with nothing. And now we can scroll through and we just want to check it. So here we hit another category, manufactured or mobile home. I'm just going to change that to MFD. And we want to check all of our data. Now I did this last week ahead of class for us, and there were a couple weird instances in there. I don't remember if I cut those out of the data file I eventually loaded. And here we find them. So we got rid of the family home thing, but now we have multifamily home / ready to build. I'm just going to replace that whole thing with multi. Okay, so this all looks okay. What I'm going to search for now are spaces. I just hit the space bar here because we shouldn't have any spaces in this data. We should just have tabs. And looking for that, we found this used to say single family home ready to build. I got rid of family home, so now it just says single. I'll get rid of anything that says that ready to build. And go back and search for space character again. And so that's fine. It's catching all the stuff up here at the top that I typed in. And that's it. There's no more spaces underneath. So that looks like I've got everything. The only real way to check if this is formatted properly is to load it into Weka, which we'll do in a minute. But now we have formatted our type neatly. And so we actually have to change this. Type is not numeric. It's going to be categorical. So we list the possible categories in the curly braces. So we have single, we have multi, we have MFD for manufactured homes, and condo. I think that's everything. Again, we'll get an error if we try to do it and it doesn't work. So I'm going to save this on my desktop. We'll call this houses.arf. Okay, I'm going to upload this for you at the end of our lecture today, so you'll be able to just go to Canvas and get this file if you have trouble, but it's worth doing this process yourself because it's a big part of what you do as a data scientist, is this kind of data manipulation. So now that we have this, we're going to try to load that up in Weka. So we're going to go to the Explorer here in Weka and then do Open File, and we're going to have to navigate to where we have it saved. And here's mine. It opened fine, so that means we didn't have any errors, which is great. Okay, so here we're looking at a whole bunch of different prices. You can see there's a bunch of common prices and then some outliers. What we're now going to do is the same kind of classification that we did last time, but we're going to look at regression instead of actually putting things into categories. So we're going to click on the Classify tab, and then we want to pick a function that we're going to use. So that's what we do here in this Classifier section. We're going to click Choose, and then we want to find a regression. So we're going to go to Functions, and then Linear Regression. Okay, this is set up to do cross-validation, and we're going to predict price, which is good. And so we can click Start, and we saw a whole bunch of stuff come out here. This is our model. So we don't get a confusion matrix here or some of the other statistics that we did for classification, because those can tell, are we correct or not? Here, we're not looking, are we correct or not? We're looking at how far off are we. We'll look at how good these models are eventually, but for now, let's actually look at the regression model, which is right here. This is exactly like what we did in class. We have our independent variables here, and then we have the coefficients here, and then this is our y offset. So what we can see is that each one of our attributes was included. Sometimes these will get dropped out. So the zip code seemed to have a negative effect. Now zip code's a weird one, right? Because it is actually a category, but we have so many that we treated it as a number. Number of bedrooms has a negative effect. So that means the more bedrooms the house has, the lower the price is. Now that's counterintuitive, and so we're going to come back and talk about why that might be. Number of baths has a positive impact, half baths does. If it's a condo or a single family home, it gets a positive value. But here, if it's a single family home, it gets a negative value. It has completely ignored multifamily homes and manufactured homes. Now that could be because they're small in the data, but it's also interesting how it's handled this. The bigger the square feet, the higher the price. We have an almost negligible coefficient for lot. So that doesn't seem to have a huge effect on the price. Okay, so let's talk about a couple things that show up here. First, this is weird, right? Type equals condo, comma, single. All the rest of these are just the independent variable names. This is done when we have a category that we're doing regression with. And so this is essentially a statement that's going to evaluate to true or false. And if it's true, it gets replaced with a 1. If it's false, it gets replaced with a 0. So here, our type is going to be, if it is condo or single, this will be 1. And if it's manufactured or multi, this will be 0. So essentially, we add in this value to the price of the home if it's a condo or a single family home. We don't add that in if it's manufactured or multifamily. Down here, if the type is single, we subtract this much, where we have already added it in up here. So it's a little bit weird, but this basically means evaluate to 1 or 0 based on what the category is. Now the next question is, why do we get this weird result where the number of bedrooms actually has a negative impact? And frankly, the fact that it's a single family home has a negative impact. That's weird. Part of this is because one of the assumptions of doing regression is that you have truly independent variables, that they don't have any correlation or covariance with each other, or you hope it's pretty small. That is certainly not the case here. So the number of bedrooms and baths and half baths, those are certainly correlated. You would not have a house that has 3 bedrooms but 12 bathrooms. You wouldn't have a house with 8 bedrooms and 1 bathroom, right? Those two are definitely related. And it's probably tied to the square footage of the home as well. So we want to think about, do we need all these variables or not? Weka will build a model that is going to try to look for this and filter some stuff out. But if you put garbage into this, you may get garbage back out of it. So let's actually see if we can personally refine this a little bit. So let's look at the error that we have down here. So we have the root mean squared error, but I like to look at the relative error. That's sort of how far off are we? Something like 75%. So that can be really big. It can be reasonable depending on what it is that you're trying to predict. We're just going to use it for a relative comparison. So we're going to look at this and we're going to see if we take out some of these independent variables, can we do better? So let's come back here. Actually, we'll go back to Excel with our data. And let's ignore the zip code. That's predictive, but it's actually categorical. So we could look at all the possible options here, but there's a lot of them. Now, we can enumerate all of those, but I think for now we'll just try leaving it out. So we have bedrooms, full bathrooms, half bathrooms, the type of the home, the size of the home, and the lot size. So the size of the home and the lot size are potentially pretty independent because there are condos in here that have really small or non-existent lot sizes. So keep both of those in. We can keep the type in, which I think is useful, but then we have bedrooms, full baths, and half baths. Those probably overlap. So let's get rid of the full baths and half baths. I'm just going to move those over. So now we have bedrooms, the type, the size in square feet, the lot size, and the price. Those are going to be the categories that we look at. So I'm going to copy that. I'm going to paste it in here. So now this is smaller. We're going to adjust our list of attributes so we get rid of zip code, bath, and half bath. So we have bedroom, type, square feet, lot size, and price. I'm going to pause this for 1 second and fix up our category names again. Okay, the magic of editing. So now we have a properly formatted thing here, hopefully. So we'll resave this. We'll come back to Weka. Reload our file here. Okay, so everything still worked all right. and come back to classify, we're going to use the same linear regression. And remember, we're going to compare against relative absolute error of 89, root relative squared error of 75. And we will be able to come back and look at this. So we're going to run it again. Didn't really impact our results so much. This is pretty much the same kind of thing. And we're getting somewhat similar results, consistent results at least. The number of bedrooms are having a negative effect. We still have this difference with condos and single-family homes. Not much impact from lot. So that's how we build a regression model. You get the coefficients just like you did before, but these regression models can get much more complicated. So some of these are not selected in here because we have data that's incompatible with it. For example, because we have this type, which is categorical, like a simple linear regression won't work. Now, I've come back to the pre-process tab because there's stuff that we can do here. For example, we can look at the type, and if I check it here, I can actually remove that, right? So I just went back before this and I went into Excel and removed some columns, but you can do that right in Weka if you want to. So I may say, you know what, we're going to ignore the type. I'm going to click on it here, and I'm going to remove the type. So now we're just going to use bedroom, square feet, and lot size to predict the price. If we come back to classify here, we now see that there's different options available. We can do, for example, simple linear regression. Run that. Doesn't give us better results. Our root relative squared error is actually higher, as is our relative absolute error. But you can see what it's done here is create this model for us that's really simple. It's just something times the number of square feet plus the y offset. So Weka will choose to ignore variables that it thinks aren't predictive. And in this case, it says, all I need is the square feet. I can ignore the lot size. I can ignore the number of bedrooms, and that gives us the best prediction. If we were to try this model with the straight up linear regression like we were doing before and start it, we actually get better performance. So this is in line with what we are looking at, though not quite as good as when we considered the type. And we can kind of try all these things out. So multi-layer perceptron is, I think I mentioned in class last week, pretty slow. And you can see the little bird flips around here while it's running. So it has built a model. It's got all of this stuff going on in the inside. This is what we do when we're doing machine learning. And we're doing a little bit better. Our relative absolute error is much better than it was on the other models. Our root relative squared error is about the same. And so what you would do if you're interested in doing this kind of regression is just try out your different algorithms, see which one gives you the best performance, and then that's the one that you would use to build your model. Let's try another one. This is a file that I have linked up for you called AutoMPG. And we can see here, we can do a little bit of exploration. So we have car data, miles per gallon, cylinders, displacement, horsepower, weight, acceleration, year, and origin. So what we want to try to do in this case is we'll try to predict the miles per gallon that a car can get based on all this other data about it. So we'll come to our Classify tab. Now here we want to pick miles per gallon is the thing that we're predicting. We're going to choose our algorithm. So we'll do linear regression and start that. And here we get much better performance than we were seeing on the houses. Our root relative error is 42%. And we can see all of our features laid out here. So the number of cylinders has a negative impact. The more cylinders there are, the lower the miles per gallon, which makes sense. The same is true of horsepower and weight. So if you get more horsepower, you get a heavier car, your miles per gallon goes down. That makes sense. The year increases it. So newer cars tend to have better MPG, which also makes sense. This origin is a categorical value that refers to, I believe, the country of origin where the car was made, but I don't have the mapping in front of me of what these actually go to. But in any case, this model is pretty good. It gives us pretty decent result. And the correlation coefficient, which we haven't been looking at, but we can check out here, that's the correlation between the actual value and the value that we predict with our regression model. That's pretty good here. It's 0.9. That's a great value to have. If we compare that, for example, on our house model, we had a much lower correlation coefficient of 0.6. Now that's still good in some cases, but not as good as what we're looking at in the MPG example. So just a couple other things to consider here. Regression models are nice because they actually give you the model. So we validated this on our own data, but we actually have the model here. So we could go out and look at the car that we have in the driveway, figure out the values for each of these things, and then plug it directly into our model and figure out what the model would guess as the miles per gallon is. Now, I think the car data that we have in here is like from the 70s and 80s, so it may not work all that well on newer cars. But in terms of interpreting the results, you actually get pretty interpretable results if you're doing linear regression models. That's not necessarily true for multi-layer perceptrons. You've got a lot going on in here, and you can't just plug your data in the way that we did before. But the simple linear regression or the regular linear regression model will give you that. Okay, so that's regression, and we've talked about doing classification. The next thing that we're going to look at is clustering. It actually has its own tab up here, and it's a different kind of thing in machine learning. So typically we talk about classification or regression, but clustering is extremely important. And what it lets us do is find groups of people or items in our data set that have similar characteristics. To use this, we're going to look at a data set from BMW dealerships. That's part of a tutorial that I will have linked up for you. And this is people who have browsed for cars. And what we're looking at here is some data from a specific BMW dealership that tracks how people walk through the dealership and the showroom, what kind of cars they look at, and how often they ultimately make purchases. So we have 100 rows of data in this sample, and each column describes the steps that the customers reached with the BMW dealership. So there's a 1 if they did the thing and a 0 if they didn't. So here's all of our attributes. This is, did they come to the dealership? Did they look around the showroom? Did they do a computer search? Did they look at the M5, the 3 Series, the Z4? Did they talk about financing? And did they ultimately purchase? So this first person just has a 1 in the first column and all zeros. So that means they came to the dealership, but they didn't even go into the showroom. This person down here has 3 1s, 3 zeros, a 1 and a 0. So they came to the dealership, they came into the showroom, they did a computer search. It has zeros for all 3 things about which car they looked at. They did talk about financing, but ultimately they didn't end up purchasing. This person has 1s in everything except for these 2 positions. So they came to the dealership, the showroom, they did a computer search, they looked at the M5, but not these other 2 cars. They talked about financing. Ultimately, they made the purchase. So what we want to be able to do is cluster these users so we can get a sense of what kind of groups of people are there. This is a really common data mining task. We often will look at something called k-nearest neighbors. You may see this abbreviated KNN. So here's a really simple little graphic that actually shows this pretty well. So you can imagine that you have some blue dots and some red triangles, and now you have this spot here. We're representing it as a green circle, but that's just because we don't know what it is. And the question is, okay, if you have a data point that's right there, which group do you put it into? Do you say that it's a blue square, or do you say that it's a red triangle, right? So you could imagine these representing men and women, or people who bought cars and people who didn't. We have a 2-dimensional space, but you actually have an n-dimensional space, really. And k-nearest neighbor says, okay, we're going to look within a certain space around our questionable data point, and we'll say draw a circle around there, and which category has the most neighbors in common with this. And we expand that search and expand that search. So if we just look in this close-in circle, this looks more like a red triangle. If we expand our circle out, then there's 3 blue squares and 2 red triangles, so it looks more like a blue square. And so the algorithm basically looks at these different neighborhoods around a certain data point and tries to figure out which group do we put the thing with. That's what k-nearest neighbors is. So there's actually lots of ways to do clustering, but that's one that you may often run into, and we're going to try something like that here. So we're going to come back to the Weka Explorer and open this file. So this is bmw.arff. This is, again, up on Canvas for you to look at. And so if we open it up, we can see a little bit of data. So for example, there's people who purchase and people that don't, not surprising. And what we're going to do now is click on the cluster tab, which we haven't looked at before. So this is actually going to let us do some clustering. We can pick an algorithm just like all the others, the other examples that we've looked at. We're going to do simple k-means here, which is kind of like that k-nearest neighbor that I was just talking about. The only thing that we would want to edit is how many clusters do we want to create. And so if we just click on that, we can look at all of this data. We can figure out how many clusters we want to have. And let's do, I don't know, let's say 4. If you do too few, you don't get a lot of insight. If you do too many, it gets far too complicated. So we'll look at 4. You know what, let's do 5. Okay, so once we've got that all put together, we're going to start this. And here we get the output of our clustering algorithm. So what we have here are our different clusters, cluster 0, 1, 2, 3, and 4. And it tells us the value for each of the different attributes. Now, these are 0 and 1 values, and so what we're seeing here is essentially what percentage of people have a 1, or what's the average dealership value, for example, in this first row. And so if we look at the first row, these are people who go to the dealership. In this cluster, 96% of them come to the dealership. In cluster 4, 0% of the people come to the dealership. So let's look at cluster number 1. None of these people purchased, which is interesting. So we have people who come to the dealership and then they kind of decline through the rest of these stages, though they do tend to look at the Z4 a little bit more than the other cars. But they show up in the dealership and then they do less and less of the following steps. Nobody ends up purchasing. So we could maybe call these dreamers, people who come in and really, want to look around but are never going to buy. Okay, here we have a cluster number 1. A decent number of these people have come to the dealership or the showroom. None of them have done a computer search, but look, 96% of them have looked at the M5. So this is a group of people who really love the M5. Only, half as many look at the 3 Series. None of them look at the Z4. They really like the M5. And half of them end up buying. So that's pretty interesting. This is a really small group here. We actually can see how many people are in each group up at the top. And so we had 26 people here, 27 people here. This is out of 100. Only 5 people show up in this group too. We can kind of ignore it. It's not likely to have a lot of meaning for us otherwise. Okay, here, cluster number 3, look, 100% of people end up financing and buying. And so this is the people that BMW really wants. Right? They want to look around at these people and see what they can do to appeal to them. They're not really interested in the 3 Series. They're interested in the 5 Series or the Z4. And we can see about 85% come to the dealership, but 85% also do a computer search once they're in the dealership. So that's an interesting data point where BMW might say, hey, these people who always buy, a lot of them are doing the computer search once they're here. And so maybe we want to make that more accessible for them. And finally, in cluster 4, if we look at this, this is interesting. 100% of these people have come to the showroom and 100% of them look at the 3 Series. Now, I'm not a BMW expert, but I did some research before this example for class. The 3 Series is kind of the entry-level BMW, right? It's an expensive car, but if you're buying a BMW, it's the cheapest one. So these people look like they're maybe interested in getting a BMW, but they're not really aficionados. They don't engage with the brand a lot at this point. They say, maybe I want one. I'm going to look at the cheapest one. I'm going to check it out and see what I end up doing. About 1/3 of them end up purchasing, but none of them are looking at the more expensive M5. The Z4 is a little bit different, so some of them end up checking that out. But they're all looking at the 3 series, and about a third of them end up buying. So you may want to figure out for this cluster, what is it that we can do to get them more engaged? For example, only a third of them are doing a computer search. Maybe that could be helpful. None of them are really interacting with the dealership, or at least not in a way that's recorded here. So there's different ways that we might look at this. Now, with clustering, this is all the output. There's a little bit of header data up here, but what you get are these clusters. There's no way to tell if they're accurate or not, because the clusters are essentially things that we make up, right? So there's no ground truth. There's no way to tell what cluster do people properly belong in. So we just have the cluster results. There is a little bit more insight that we can get. So something that we haven't done yet, but you can, is you can right-click on the result list here. If you're on a Mac, you actually have to do Option and then click. So it's not the normal Control click on a Mac, but Option click. And then you can select Visualize Cluster Assignments. And this is going to give you a visualization to look at the different ways that things cluster together. So for example, we have an X and a Y axis up here. So we could say plot people who have looked at the M5 with people who actually end up purchasing it. Now we can't see anything here. There actually are X's in the corners. And why are those X's there? Well, because the people who looked at it either get a 0 or a 1. And if they bought it, they get a 0 or a 1. And so everybody's just going to be in a corner. They'll be in a 1, 1, a 0, 0, or a 0, 1 corner. So we can adjust this slider called Jitter, which kind of adds some noise in and spreads people out. It's meaningless. It's just noise, but it allows us to see things a little bit better. And so if we increase the jitter, we can kind of see where everybody lies. I'm going to really spread it out. And this is useful not because it's meaningful that this X is up here as opposed to in the corner. They all actually belong straight in the corner. But because we can see different points of where the groups lie. So if you look down here, we have cluster 0 is blue, cluster 1 is red, and then we have a green, a teal, and a pink. And you can see where these lie. So for example, up here, we have a lot of pinks and teals for clusters 3 and 4, but there's no blue, there's no red up here. Maybe there's one red, it's hard to tell. Here we have a lot of red and teal. There's some green ones mixed in down here, though I think that's a really small cluster. Here we've got some pink and some blue ones, but there's no red ones in there for sure. Doesn't look like any green or teal ones. And so this allows us to see where do our different clusters tend to fall based on this kind of visualization and the clustering that we did. Okay, so let's look at one more example here. We're going to open a file now called BMW Training, again, which is linked up for you. This is BMW data. Let's take a quick look at this. Similarly from the dealership, that just has a little bit of information about people who responded to a marketing effort. So we have their income bracket from low to high, if this is their first purchase, about their last purchase, and if they responded to something that the dealership sent them. The first and last purchase, these are numeric values indicating when they bought their first BMW and when they bought their last BMW. So they could be the same, they could be different. For example, if we look here, this person is income bracket 4. They bought their first BMW at this time, which I would guess is 2002 in October. And then they bought their last one in 2006 in January. We'll interpret it like that. I think that's right. And then did they respond to an offer from BMW? In this case, it's an extended warranty offer that was sent to them. And so we have this set of responses, and what we're going to look at is how we can use clustering like we just looked at, but to do classification. So this is just a little bit more advanced look at the algorithms. So we're going to come over here to Weka. We're going to open that file, BMW Training. And what we're looking at here is the income tax brackets and then whether or not each person responded. So we're going to first take a look at doing some classification with that. So come over to Classify, and we're going to pick our algorithm here. So we're going to go into Lazy and then IBK. This is a k-nearest neighbors clustering algorithm that we use to do classification. So just like that graphic that we just looked at, we essentially have people who responded and people who didn't. We have some ground truth for that. And then we want to get some new data and be able to classify where each of those data points lies, which in this space that we have. And here it's a pretty simple space: income tax bracket, first purchase and last purchase. So in this three-dimensional space, which data points is a new one closest to, and then we use that to guess which class it goes into. So we have all of our data here. We're actually going to use a separate training set for this. So we have this option, use training set, and we're going to use that to build our model, and we'll check it out on separate data later. So what this means when we pick use training set is that we're going to evaluate how good our model is based on the data that we're training on. So this can be a little bit optimistic, but we're going to check it out later to see how it works on a test model. So we've got k-nearest neighbors. We're going to just evaluate on our training set here, and we can run it. And here's the output that we get. So we're classifying pretty well. Our accuracy is 88%, which is great, almost 89. Our area under the curve is 0.972. That's exceptionally good. So let's actually compare that just to a different classifier, just as an example that we have to compare to. So let's pick a tree-based algorithm like we did before. And so if we run that, our tree-based algorithm didn't do nearly as well, even evaluating on the same training set. About 60% accuracy. Our area under the curve is 6.16. Our k-nearest neighbors, phenomenally better than this. And so it allows us to see that clustering can do much better for us than if we're doing simple classification. So you can actually play with this yourself. If we come back up here to IBK and click on this, we can see that we're using a k-nearest neighbors classifier, and we can play around with some of the values in here. How many batches are there, that kind of thing. How many neighbors are we looking at? So for example, here we're looking at the one nearest neighbor. So the k-nearest neighbor is how many of our nearest neighbors are we looking at. This one finds the one person in this case that's most similar to us in the space, that's closest to us in the space, and puts us in that category. We could say, well, let's look at the 3 people that are closest to us to make that determination. So if we're looking at 1, we get 88% accuracy, 0.972. If we run it separately with the 3 nearest neighbors, we do remarkably worse, down to 73%, and our area under the curve has decreased as well. So what that means is that in a data set like this, and in fact in a lot of data sets like what you would get from Amazon or Netflix, or where you're doing recommendations, for example, the one person who is most like you is probably most representative of your tastes. And if you start looping in more people who are a little bit further out from you, it actually gets you further away from people who are similar to you. So that one person actually ends up being most predictive. But that's not always true. So it could be, for example, that on Netflix you have pretty distinct groups of movies that you like, right? So it may be, I like, for example, documentaries and kind of supernatural horror movies like ghost shows and haunted house movies. And so it could be that the person who looks most like me on Netflix shares a lot of my ratings for the supernatural horror movies, but they also like the kind of tortury, violent horror movies, which I don't like at all. And so that one person may be very close in my tastes on some things, but they don't do well predicting for others. Where if I expanded my search a little bit, I may loop in people who also liked documentaries and people who would give lower ratings to those kind of violent horror movies, and my taste gets teased out a little bit better. So playing with that model is really going to depend on your data set, what the best choices are, and you want to try things out and see what gets you the best model. Once you do that, you can actually run it on test data. So we can put this back to 1, and just as a reminder, if we rerun that, we get our really good results. And then we can test it on a supplied test set. This I've also provided to you. It's called BMW test. And if we run that, we can see that we get much worse performance, 56% accuracy, our area under the curve 0.583. And so we may try doing some more tweaking to make that better. So let's up our k nearest neighbors to 3 and see how that impacts things. Not too much. It stayed about the same. So this teaches us a couple interesting points. One is that when you're evaluating on your supplied training set, you can get remarkably different results than you will get on an actual test set. You can very much overfit to the data that you have, and that we clearly see here. At the same time, that doesn't necessarily mean other things will do better. So what we saw here, using our 1 nearest neighbor, our k nearest neighbors with an example of 1, our correctly classified instances were 56, our area under the curve was 0.583. Now if we compare that to J48, these are the results that it got evaluating on itself, but we can run J48 on our supplied test data. I haven't actually done this before, so we just want to see, does it do better? And if we run that, it actually ends up doing about the same. So here, 55% accuracy, 564 area under the curve, 56% actually, 582 under the curve. So it ends up performing exactly the same as the k nearest neighbors, pretty much, even though the evaluation on the training set showed a big difference between the two. So what this really illustrates for you is, 1, be careful about evaluating on your training set. You cannot report that as the accuracy of your algorithms. You have to report on something else. And 2, just because an algorithm and a model looks good when it's evaluated on the training set doesn't necessarily mean that it will perform superior on the actual test data. Okay, so that's it for Weka. I'm going to link you up some of these tutorials. You have all these data sets, and it's something that I want you to kind of play through and try yourself. But now you have the fundamentals of the different algorithms, regression, classification, and clustering, and some of the ways that you can use those to look at your data. On top of that, you know how to interpret the results, so you know how to use the actual outputs of your regression, how to look at the outputs of your trees or your rule systems, for example, for classification, and then a little bit how to interpret the clustering that you get from running those algorithms. In addition to that, you can look at some ways to visualize these results. And that's something that you can explore around with. There are visualization options in the same thing by right-clicking on the results that you see in classifiers, for example. We haven't looked at these, but you can visualize, for example, the errors that your classifier gets and do the same kind of analysis here. There's a lot of features buried in Weka. What I have shown you here are what you're going to use 95% of the time. I don't think I've ever really had to go much beyond what I've taught you here. So now you have some good fundamentals. I'm going to post up an exercise for you to work on just to, you know, kind of try something different. And yeah, that's it for machine learning. You now have all the basics you need to format your data, get it in, and try a whole bunch of different algorithms on it, and to understand their outputs in the models.